Hi, this is Erin Nichols, and I'm going to be reading a PowerPoint presentation that I'm going to read tomorrow, and it is done as a part of a group project. It focuses on the literacy outcomes of children with early childhood speech-sound disorders and the impact of endophenotypes. This is a study that was published in 2011. The hypothesis for this study is that if endophenotypes are influenced by genetics, then childhood speech-sound disorders and later developing language impairments and/or reading disorders will be demonstrated. We must define that endophenotypes connect genetics to measurable and observable characteristics. In the case of the study, the endophenotypes are SSD, LI, and RDs that are being genetically analyzed. The determination of participant eligibility. For the people to participate in the study, they must meet a few requirements. They have to bilaterally pass a hearing screening at 20 decibels. They must have a normal IQ score of at least 80, which is done by the Wechsler Preschool and Primary Scale of Intelligence. They must pass the oral speech mechanism screening exam, the Goldman-Fristow test of articulation score below the 10th percentile. The final component is that they must go through the Kahn-Lewis phonological analysis test. There must be a minimum occurrence of 4 phonological processing errors and a severity rating of 3 to 4, which is moderate to severe. The methods within the study can be broken into 2 portions, the designs and the participants. We are going to focus on the participant data first. We start with 152 program children falling between 4 and 6 years of age. They have moderate to severe speech-sound disorders, and they were referred by SLPs. Of these, 105 programs were followed through school, ages 7 plus, and then reassessed. There were 47 proband lost to attrition. All siblings of the proband children were invited to participate in the study as well. There are 256 siblings, and they were assigned to a typically developing or an SSD group. The designs within the study are a longitudinal pre-test and post-test design. They are pre-early childhood assessments and post-school age assessments. The SEM analysis performs on probands and siblings. The N is 408, and that is also the baseline data. The SEM models include the AIC, BIC, and SRMR. The following assessments were then performed. These were split based off of the age of the child. The early childhood assessments were for children that fall between 4 and 6 years old. They went through an oral motor skills assessment, a phonological awareness assessment, a phonological short-term memory, a vocabulary, and a speeded naming assessment. The school age assessment, which is for children that are older than 7, went through a reading and decoding assessment, a spelling, and a written expression. The results of the study indicate a genetic linkage between speech-sound disorders and chromosomes 1, 3, 6, and 15. The phenotypes with genetic links to speech-sound disorders are measured and observed on chromosome 1, 3, and 15. Chromosome 15 has GFTA and PCC. The SEM analysis demonstrated that endophenotypes were linked to speech-sound disorders and language impairments with school-age children. The conclusion of the study is that researchers observed the following endophenotypes: phonological awareness, phonological memory, oral motor skills, and expressive vocabulary. Based on the study's results, we can conclude that genetic linkage of endophenotypes can be early indicators of speech-sound disorders, which can later develop into a language impairment and/or reading disorder. With the evidence found in the genetic analysis, researchers confirmed their hypothesis and can conclude that there is a genetic influence on spoken language skills. These research advancements can allow for early intervention and treatment approaches which can aid in the prevention of atypical development. The implications for this study are: the findings suggest that shared endophenotypes and common genetic influences affect early childhood speech-sound disorders and later school-age literacy. Genes for SSD may include multiple endophenotypes, which are oral motor skills, phonological awareness, phonological memory, processing speed, and expressive language. The genetic linkage can impact the practice of SLPs by allowing earlier identification for speech-sound disorders, which can lead to earlier intervention. This relates to clinical practice in that the genetic breakthroughs have created a breakthrough in diagnosing and identifying speech-sound disorders. The health professionals can identify the presence of chromosome mutations in infants at early ages and refer these individuals to SLPs. The SLPs will receive referrals at younger ages, allowing for earlier intervention. Early intervention is key to prevention. The early intervention can decrease the long-term impairments or effects of a disability by identifying it as soon as possible. The advantages to this study are that it provides early intervention, which can prevent the development of reading disorders, and it limits comorbidity. The genetic identification of chromosomes attributes speech-sound disorders to known origins and causes. Knowing the cause of an SSD can then allow SLPs to identify and treat these children at younger ages. Strict eligibility requirements ensure findings are not biased due to comorbidity from other known causes of SSD. The disadvantages to this study are the threats to the internal validity. Attrition occurred within test 1. There were 152. Within test 2, there were 105. The study limitations are that SCM genetic linkage analysis was not performed on identical data sets. This relates to the textbook in that in 2001, the FOXP2 gene was identified as a known contributor to speech-sound disorders. This is located on the 7th chromosome. There are 5 chromosomes that are associated with speech-sound disorders: chromosome 1, 3, 6p, 7, and 15q. It is worth noting that chromosome 7 is responsible for cell division and growth, and it contains genes for taste and smell receptors. FOXPI is located on chromosome 3p14. The strongest association with speech-sound disorders, as well as ASD and cognitive impairments.